Now I'm going to be moving to the last part of our last chapter of our last unit in maths. So C4 chapter 6 integration, and the last part is about areas and volumes, and this is the 8th part. If you remember at the very beginning of the tutorial about integration altogether, I used areas and volumes to explain what integration is. So it's very obvious to you now why we'll need to study volumes and areas when we're talking about integration. So integration can be used to find the areas and volumes of shapes. So the area of a region between areas of any region is going to be, if we want to draw a graph here, and if I say we have a certain curve that looks this way, and I want to find the area between this part and this part, then this is our A, B, and to each part here we have a corresponding value of y. Now if we multiply, what we're doing is we're trying to find the area under this region. So what we're going to do is we're going to multiply whatever's on the y by whatever's on the x. Why? Because if you know about the trapezium rule, or according to the trapezium rule I mean, when you're taking very small strips here, you're multiplying y by x, you're finding the area of this rectangle, and then you do the same for each rectangle after it, and then you find the sum of them, and this is actually what you're doing in integration. So in integration you're adding these very tiny rectangles, which are the tininess is described as the width of the triangle, which is dx, and you're multiplying that by the values on y. This is why when we are trying to find the area of any specific area, what we're doing is we're multiplying y by the very small difference on x we call dx, and we're finding it from a to b, and these are our boundaries. Now note that if we do not have the a and b like we did in all the previous examples, this is called the indefinite integral. But here when we have barriers, this is called definite integral. It means it has an end. It means it will not give you a certain set of functions like we had where we added the general c. No, this will give you an actual number, a constant. This will give you an answer, the exact area. Then this is for area. So what we're doing is we're integrating y in terms of x from the boundaries a to b. So and then I'll explain volume, and then I'll move on to examples. Now if we want to find the volume, instead what we do in order to find the volume of an area is that we're rotating it. Why? Because we're trying to give it a third dimension. So let's say you have those two lines here, and we know that this is the area between the two lines, this area here, and let me just shade it all, and that's it. Now if I wanted, this is just a 2D plane, ignore the actually third dimension because I'm writing in solid font, but this is just a 2D plane. Now if you wanted to have a third dimension, what you can do is you can rotate it about an axis. So let's say here I actually wanted to rotate it about our y-axis. So what we're going to end up having is a shape that is in third dimension, because it's going to be rotating. It will be something like this disc here, with the hollow, it's hollow in here, but from the outside it appears to be complete because it just continues to meet inside. And this is actually all colored here, this is all actually there. Excuse the drawing, I can't exactly draw in 3D on it in here. I need to do shading and such, but whatever. Anyway, so this is going to be a 3D shape. This is actually colored, but at the back. Anyway, so let's just ignore the whole thing. Anyway, this will be a 3D shape. You can just imagine it or draw it, and there are actually computerized versions where you can see the 3D diagram. But what we're saying is we're rotating it, and because we're rotating it, we are trying to we're turning it in a circle around something. And because of that, when we want to express volume, what we do is that we sort of use the circle formula, because it's, if you know the area of a circle, is actually equal to pi r squared. And this is what you're doing. You're taking the 2D area on top and you're multiplying it by the wides here. So you're multiplying it by your actual lines. So what you're doing is your radius starts becoming your y, because you're going to be taking your slices to be like this here. Or if you take it about the x-axis here, like this, then your slices are you're going to have a 3D shape which you can cut into slices like this. And this is actually a disc shaped, and this is our dx, and our radius becomes dy. So this is why when we're trying to find the volume, what we're doing is we're integrating the area of the disk, of the circle, which is going to be pi integration of y, which is our r, squared dy. These things can get a lot more complex if you go, into dx. These things can get a lot more complex later on as you get into calculus 2, but for now it's just this simple. You're going to apply this formula and you're going to solve. Now that we know both the formulas for area and volume, we can actually take examples. I'm going to give you here an example. The example states that let y equals to 2 plus sine x, and know that and the boundaries are x1 is 0 and x2 is pi over 2. The first part of the question says find its area. We know that our area is going to equal to integration of just y. So it's going to be 2 plus sine x, and this is going to be dx. And that will simply simply going to give us 2, and of course from our boundaries, 0 to pi over 2. This is going to be simply 2x, and integration of sine is negative cosine x. Now we put this here between our boundaries, which is 0 to pi over 2, and what we do is we take upper boundary minus the lower boundary. So this is going to be 2 into pi over 2 minus cosine into pi over 2, and we're going to subtract from that 2 into 0 minus cosine 0, which is 1 by the way. So this is going to give us the answer to be pi plus 1. This is our area. The second part is that we want to find the volume by rotating it about the x-axis into pi radians. So we're doing a sphere again. So we have this graph. I actually always recommend that you draw your graphs if you can. So this is actually sine x but plus 2, so this is something like this. Anyway, when we asked to find the area, we were finding this area. Now we're actually rotating the whole thing about the x-axis. So what we're going to do is that we're going to apply our volume equation, which is going to give us pi into 0 to pi over 2 into y squared this time, so 2x, it's actually just x, I guess. What was it? It's 2 plus sine x all squared. So what we're going to do is that we're going to expand this here into equal to our pi into 0 pi over 2. This is going to be 4 plus 4 sine x plus sine squared x, and that will be dx. And then finally we can express this, we can solve this to be equal to, this is going to be 4x, this is going to be minus 4 cosine x, and this is going to be plus sine 3. How do you integrate sine x? And then you're going to integrate sine squared x, which is actually it's actually a long thing to do, which because you're going to express sine squared of x in cosine 2x format, and it's going to be half minus cosine 2x over 2. So half minus cosine 2x over 2. You're using trigonometric identities, and you're doing it from pi over 2, from 0 to pi over 2. You're going to replace, you're going to solve, and in the end you're going to get the answer, which is 9 over 4 pi squared plus 4 pi. Note here, very important notice, that throughout this chapter, all integration can be performed on the calculator to check your answer. So don't let the examiner have the chance to deduct marks when you know how to check for yourself. And that would wrap up all our integration chapter. We've done. I'm going to add one more tutorial to summarize all this together.